Alright gang, here we go. This is for Chem 1, Unit 14, Part 2. We're going to talk about the common ion effect. Alright, this stuff's kind of tricky, but really if you just think about it in terms of Le Chatelier's principle and kind of things we've been talking about all year, you'll be fine, I think. Probably. I hope. So consider the equilibrium system of acetic acid. So acetic acid, so think about your acid-base equilibrium. We talked about this, it's been a while now. But so if you have acetic acid, that's CH3COOH, right? If we put this in water, we know that an acid-base system, right, is really just about donating or accepting protons. All right, so your acetic acid is going to act like a proton donor, right? So it's going to donate the protons. Now, remember, acetic acid is a weak acid, so it's not going to completely dissociate. So we're going to throw in this equilibrium. It's simple here. So if it's a weak donor or a proton donor, it's going to form. It's going to lose its proton, so it's going to become acetate. All right, CH3COO minus, and then it's going to give its proton to the water over here, so it'll become H3O plus. All right, so that's your equilibrium system of acetic acid. All right, and now it says what shift would take place if you were to add some amount of sodium acetate? Well, we know sodium acetate, it looks like this. It's sodium with CH3COO, all right? And if we put that in solution, we know that's soluble, and so that means it's going to dissociate. It's going to form sodium ion and acetate. So just for a second, take a step back and think about what's going on. You have a beaker full of acetic acid, and this acetic acid automatically forms this equilibrium, right? Where some of the acetic acid donates protons to water, not all of it because it's a weak acid, but some of it. And it's going to donate its protons to water to form acetate and hydronium. All right. Now, at the same time, you have this beaker that's at equilibrium of this acetic acid, and then you take a spoonful of sodium acetate and you dump it into your solution. That sodium acetate, because there's water in that solution, is automatically going to dissociate into sodium and then acetate. All right, and so that means this acetate is going to match up with this. You've got this what's called a common ion between both of these systems. All right, you've increased the concentration of acetate by adding sodium acetate to your solution, and because you've increased that concentration, that's going to affect your concentration of your equilibrium, and so it's going to shift. It's going to make this whole thing shift to the left. So if we add sodium acetate, our whole thing, based on this Le Chatelier's principle, is going to shift to the left. All right. Now, what would happen to the pH? Now, remember, your pH is really a measurement of the constant or the acidity of your solution. We calculate the pH by taking the negative log of the hydronium, the concentration of the hydronium. So really, our pH is going to give us an idea of what happens to the hydronium concentration. Remember, if we're acidic, that means we have a really low pH, and if we're basic, that means we have a high pH. Okay, so originally our acetic acid system, depending on the concentration of the acetic acid, could be somewhere between like 2 and 4, right? So let's just say it's at 3. All right, if we add that sodium acetate, are we going to get lower, more acidic, or higher, less acidic? Okay, well, we know that our whole thing is going to shift to the left, which means we're going to have less hydronium, okay, because it's shifted away from that side to counteract the addition of the acetate we've added. And so we're going to have less hydronium, so that means the hydronium ion concentration goes down. So that means we are less acidic. Remember, the hydronium is really what we're looking for. The bigger that is, the more acidic we are. So we're going to be less acidic. All right, so because we're less acidic, that means our pH will go up. So the pH will go up. So the common ion effect is defined thusly. It says the phenomenon in which the addition of an ion common to two solutes brings about precipitation or reduced ionization. So that's exactly what we just saw. We dumped in sodium acetate and our thing was reduced in ionization. Okay, it could also form precipitation like here. Okay, so imagine you have a saturated solution of sodium chloride. So sodium chloride is table salt. You've got a saturated solution, so the solution is holding as much sodium chloride as it possibly can. And then you take hydrogen chloride gas and start bubbling it through this solution. Well, as it bubbles through, the hydrogen chloride will start dissolving in the liquid, right? It's going to dissolve, this hydrogen chloride gas will dissolve into hydronium and chloride anion. Okay, and now look at this. You've got a common ion between the chlorine and the chlorine right there, between these two things. Now, so if your chlorine starts dissolving more, that raises the concentration of the chlorine. And remember that your sodium chloride was it was saturated. You couldn't dissolve anymore. So now that we've got extra chlorine, you're gonna start precipitating sodium chloride in the bottom of your solution. So you're gonna have extra sodium chloride in the bottom because you've precipitated this thing. All right, and so that's really what it comes down to. Okay, so we've seen that the common ion effect can affect the amount of ionization, essentially changing the pH. Okay, and then it can also make something precipitate. All right, and depending if something's saturated, we can add a common ion from something else and make this other thing dissolve or precipitate out. All right, so that's about it for the common ion effect. Not too terribly difficult, just kind of an extension of Le Chatelier's principle. All right, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.